We're going to continue our discussion of synchronization, and unfortunately we're only going to be able to scratch the surface of it. It used to be that we had CS141. I don't think that's a class that's taught anymore. Anybody here heard of it or have taken it? No. So they started offering it when I was an undergrad, and it was really good. It actually runs you through a lot of these kinds of details, which is really valuable. And now that we don't really have a class like that, you kind of have to pick it up as you go. So I'm going to cover as much as I can in this lecture, which is not a lot, I'm afraid. We're going to cover some really basic things. And then when we start getting into some of the more concurrent and complex parts of the operating system implementation, i.e. virtual memory page table management and file system buffer caches and things like that, we'll take a lecture or two to actually walk through the implementation of those things from a concurrency perspective so that you have a better sense of how to approach them. Because, again, it all comes down to the question of what can interrupt what things might all be going on at the same time, how do I synchronize access to things so that everything works properly and successfully. That really is all it comes down to. It's just that, you know, when you're a beginner with these systems, you don't necessarily realize all of the things that are going on at the same time and how to solve those problems. So I'll try to spend some time talking about those in the future. But we did introduce this concept of a critical section. Again, this is probably not new to you, but you have race conditions, which are just pieces of code where the result of the code or the outcome, the state after the code executes, depends on who gets to it first. Okay, so that's why we call it a race condition, because whoever wins the race seems to have the biggest impact on the state. And so we need to prevent these race conditions by imposing mutual exclusion on certain regions of the code. And those regions are called critical sections. So yeah, critical section and then mutual exclusion. These two concepts are very closely linked. Because obviously mutual exclusion appears in other contexts as well, but mutual exclusion is just a mechanism by which we can enforce a critical section. Okay? So you can imagine the critical section is going to be enclosed by some mutex lock, some mutex unlock, and so forth. Okay, and there's a lot of different tools. We're basically going to talk about just a couple. We already got to see how a mutex is implemented in CS24 in assignment 7, so I expect that you probably understand the concept. You have some atomic bit test and set, you have some atomic exchange operation that the processor ensures is atomic, and then you can use that to build a mutual exclusion mechanism. So not terribly sophisticated. On top of mutexes, you can build semaphores. On top of mutexes and semaphores, you can build condition variables, read-write locks, a lot of other very useful things. So we're not going to spend a lot of time talking about the more advanced mechanisms like read-write locks and condition variables because they tend to be relatively straightforward extensions of these things. But like I said, these locks will generally block threads from executing. So we get passive waiting, which is really what we want. We don't want spinning. We do it sometimes when we have to. And remember, spinning tends to be the recourse of interrupt handlers running on multi-core systems because we kind of have to. Okay, so yeah, so that's what I was just talking about. Let's see, so there are purely software solutions, which is one of those really surprising results, but this was actually one of the first algorithms. It wasn't the very first, but it's very representative of how to ensure that two programs can coordinate access, or two let's say processes or some pieces of code that are executing that want to enter into a shared critical section, how they can actually make sure that mutual exclusion is ensured. And this is the outline of the implementation. So while true, the outer while is just these two programs are trying to do something, and it's very simple. We've basically stripped away all the non-relevant pieces of the program. And you state your intention to enter the critical section by setting a flag. Notice I don't actually state it here, but flag is an array with two elements in it. That's all we have. And so we have flag I and flag J. That's all we really have. And we say, I want to go into the critical section, but it's the other guy's turn. So they get to go first if they would like to. And then we busy wait in a loop. Okay, so that's the first strike against this approach, but you can take it and turn it into passive waiting, not terribly difficultly. If you have things like a halt instruction and interrupts and so forth, you can certainly do that. A few of you did that kind of thing on the second project. So as long as it's the other guy's turn, then I don't go into the critical section. But once one of these two conditions becomes false, then I can enter into the critical section because I know either the other guy said I can go into the critical section, or it's not their turn. It's my turn, so I can go into the critical section. Okay. Once I finish, then I flag that I am leaving the critical section, and then I go on and do my own thing. Okay. So this is Peterson's algorithm, and I'll mention that there's a couple of other ones that are representative of this. This is obviously very limited. We're talking two processes or two pieces of code that could perform things. That's not very exciting. And we have busy waiting. So this is a very primitive approach. But like I say here, PI can only exit the while loop, that is, the inner while loop, which prevents us from entering the critical section. We're not allowed to enter the critical section as long as, like I say here, well, let me see how I state this. I want to get the sense correct. Yeah, so PJ is outside the critical section, so flag J is false. So you can see that the flag value basically brackets the critical section. I set it to true when I want to enter. I set it to false when I'm out. So if the other guy's flag is false, they're not in the critical section. I can go ahead and do it. I can enter into this critical section. Or it's my turn. If either one of those is the case, then I can go ahead and enter the critical section. Okay? And we're not going to talk very much more about it. There's proofs of this algorithm's correctness and so forth, but we're not going to spend very much time on it. It is a representative example, and so when you hear people talk about software-based mutual exclusion, they frequently refer to Peterson's algorithm. There's a few other ones, like I have here. I can't remember the details of all of them, but they have variations to them. Now I can do more than two processes, blah, blah, blah. You have various details like that. Okay? But yeah, they all work basically the same thing. So there's two problems to this approach. The first one is an obvious one, that we have to busy wait instead of passively waiting. Well, that's just because we don't want to have all the complexity of interrupt handling and blah, blah, blah. Okay, if we had those mechanisms, we could easily make this passively wait instead of busy waiting. Okay? So that's not really the big issue. There's another much more serious issue, which is that on all modern processors, this will probably fail if we just code it up as it is. That's really bad. The reason why is because a lot of parts of our stack basically like to reorder instructions so that we get more optimal execution. Okay? So if I have a compiler that tries to optimize, we're running on a superscalar processor, so I have multiple components, multiple ALUs, maybe multiple addressing logic, multiple other components of my processor, then I need to be able to schedule instructions to maximally use all of those things. That may mean doing them in a different order than the program actually says. And in general, compilers are pretty clever about trying to make sure that when it picks a reordering, that the result will be the same. But the compiler has no idea about concurrency. Multiple things happening at the same time. It kind of views the program as a single sequential flow. So out-of-order execution is good in most cases, but in a few cases, it's terrible. Okay? And then processors themselves also reorder instructions, which is even crazier. Okay? The Intel processors are more than capable of doing that now. So when we have these kinds of situations, you can easily end up with scenarios where out-of-order instruction execution or instruction reordering causes this software-based solution to fail. And that is no good. So thankfully, we have hardware-based solutions. We all know how to do those kinds of things with lock instructions and so forth. Not terribly complicated, but it turns out that those are actually a subset of a more general approach, which is that sometimes we have to make sure instructions actually execute in the order that we specify them. This is particularly true when we get into concurrent programming. When I want to do this thing, and then that has to finish, and then the next thing is allowed to start, and I'm never allowed to reorder those things, then I need to have some way of enforcing that. Okay, so barriers are a great example. Like I say, our previous software solutions don't work in the context of out-of-order execution, so we simply prevent out-of-order execution by putting a barrier between two operations. Okay? A barrier simply means everything before the barrier has to finish before anything after the barrier is allowed to start. That's all we really mean by a barrier in this context. Okay? I mentioned multi-threading barriers, not a terribly complicated topic, but I'm not going to waste the time to talk about it right now. You can ask me after class if you're curious. Okay? But in this context, we're just making sure that everything finishes before anything starts after the barrier. Okay? Now, there's kind of two kinds of barriers. We have barriers at compile time and we have barriers at runtime. Because we have two places that instructions could be reordered. We could reorder them in the compiler, we could reorder them at compilation time, we could reorder them at execution time. So we have two places, and the compiler situation is fixed with an optimization barrier, which you can see is a very simple barrier. It actually does nothing. If you look at it, we say, I want to emit some assembly code, and then you emit no assembly code. But then what you do is you tell the compiler that everything changed. It has no way of optimizing anything across that boundary because it can't make any assumptions about the state of memory. So let's say it sucked a value out of memory into a register, and then it was using the register to do the intermediate computation. And then maybe it would like to assume that that register value is still the same. Well, when you say that all memory has changed, then the compiler no longer can trust the value in that register anymore. Now memory may have a different value than the register holds, so it has to go and fetch it again. So that's the concept of an optimization barrier. Really simple, right? And so you can put barriers into your code. Thankfully, you guys don't have to. I just want to state this up front. This is really important for understanding concurrency on these systems, but it is thankfully not required for you guys. I would love to give you an assignment where this was required, but it would probably be several weeks, and you'd be pulling your hair out, and we don't have time for it. So sad we don't have semesters, right? So anyway, you just make sure if you have some part of your program that needs to be completed before the next part can start, you just insert a little barrier there. And then you can trust that the compiler will not reorder instructions across that boundary. Okay, so that's the idea behind an optimization barrier. Okay? Of course, just because you say the compiler is not allowed to do it doesn't keep the processor from doing it. So we have to make sure we also tell the processor that it's not allowed to reorder across that boundary as well. So optimization barriers are necessary, but they're not sufficient. So memory barriers basically prevent instruction reordering in various ways at the processor execution level. Okay? Like I say here, all the instructions before the memory barrier must be completed before any instructions after the barrier are allowed to commence. Okay? So that's pretty easy. And like I say here, when you want to emit a memory barrier instruction at the compiler level, so you put that in there so that at runtime the processor knows, okay, you're not allowed to reorder operations across this boundary. You better also put an optimization barrier there so that the compiler also knows to reflect that. So you have them in both places when you do memory barriers. Okay? And there's various kinds. Let me see if I actually talk about it. Yeah, I do. So you have read memory barriers, which basically mean you cannot reorder reads. So let's say I read A and then read B. And you'd think that most of the time it doesn't matter if I read B and then A. But if I read A and then based on the value of A, I do something with B, or I don't do something with B, then if I reorder those operations, I might have a problem. So I have to make sure that I put a read barrier there. Okay, so read memory barrier specifies a constraint on reads. Write memory barriers specify a constraint on write ordering. And then you have a general barrier which will prevent all reads and writes. I should say before the barrier, all of those reads and writes have to complete before any reads or writes after it are allowed to commence. Okay, so you have basically three kinds of barriers you could think about. Okay. There are cases where single core systems don't require barriers. If I remember correctly, IA32 is actually pretty nice about reading memory. Like IA32, so this is another thing that's specified in an instruction set architecture. Does the processor reorder reads? Does it reorder writes? And IA32 is actually pretty nice as far as reordering things. Like, it's a very well-behaved processor. It doesn't do things that are totally crazy out of control. It might reorder reads. It probably won't reorder writes. and it definitely doesn't reorder certain other things. And you can read all about that in the IA32 manual. Not every processor is that well behaved, it turns out. The DEC Alpha is like the most notoriously badly behaved processor ever. And part of the reason why is because it has 2 data caches on the processor that aren't necessarily always kept in sync. So you might have one read, and you get a value, and then you do a write, and it updates the one cache, and then you do a read of that value, and you see the old value still. Okay? And it's allowed to do reordering of things. So it's like the DEC Alpha is terribly badly behaved, and you have to be very careful when you're doing these kinds of concurrency operations to make sure that the processor does things in a way that makes sense. You can look it up and read about it. It's funny because Linux's concurrency model is kind of defined by the DEC Alpha processor and how bad it behaves, even though IA32 is much better behaved. Because, again, Linux has to sort of try to handle the worst case. You know, it's got to go to the lowest common denominator, support that, and then everywhere else, it may not even have to emit instructions to get various kinds of ordering guarantees. So that's just one of those fun things about trying to support many different processors. Yay, right? Okay, enough about that. So IA32 has a couple of instructions that a couple of 3 instructions you can use. So you have lfence, sfence, and mfence, which you can use for read, write, or all general purpose memory barriers. Okay, but those are not the only ones that actually impose barriers. This is only if you are doing specific things in a specific section of your code. If you happen to be doing other operations, like you have an instruction prefixed with a lock, that operates as a barrier, which is a good thing. IRET operates as a barrier so that you know that the interrupt handler's work is all finished before you go back to whatever code you pick up with, so you don't have to worry about reordering across that boundary. Okay, so there's various things that IA32 does to try to make sure that life isn't completely miserable for people trying to write correct concurrent programs. Okay? And when you have multi-core systems, it's also really nice, because if you have a fence, you may say, well, what if that's only on that one processor? That would be pretty lame. And so the processors, I should say all the cores in a multiprocessing system or in a multiprocessor system collaborate to make sure that when you have a fence, everybody sees the same behavior. They'll see the old value and then the new value. They won't see the new value, then the old value, or some other weird arrangement of circumstances. Okay? So again, not every architecture guarantees this, but IA32's guarantees in this area make it a lot simpler to write concurrent programs, which is, it's hard enough as it is, right? Next time when we start talking about some of the really clever advanced concurrency mechanisms, you'll be like, oh, okay, yeah, it's really nice that IA32 makes our lives simpler. Of course, we also mentioned previously that disabling hardware interrupts is always an option when you want to prevent concurrent access. You're probably doing that, hopefully somewhat frequently, but not too frequently. It's like, where's the balance? Is always an interesting question. But this is if you want to prevent interrupt handlers from accessing state that you are also manipulating. So I'm doing it from process context. I want to make sure that the interrupt handler can't manipulate my shared state. So I turn off interrupts while I manipulate my shared data. And then I turn it back on, and now the interrupt handler is allowed to access it. Okay? The interrupt handler is not allowed to acquire a lock, so they should assume that they can have access to it. If you're in the interrupt handler, it's because nobody's accessing the shared data structure. That's kind of the presumption inside the handler. Okay? There was something else I want to say about this, but I forgot. So we'll see if I remember. Okay, so you all know how to enable and disable interrupts, STI and CLI. So set the interrupt flag, clear interrupt flag, and so forth. Of course, this will not disable non-maskable interrupts, but those tend to be pretty infrequent. Okay. And yeah, this is important. When you disable interrupts, it's disabling them on one processor. It is possible to turn off interrupts on all the processors, but it's a terrible thing because basically then all the processors in your system stop dispatching, and so you're going to see sort of an increased latency to responding to interrupts, and that's bad. People will perceive that. And so typically you try to design multiprocessor operating systems to only have to disable interrupts on the local processor if you ever really have to. So that's kind of a really important detail there. I'm trying to remember, there was something kind of important that I wanted to mention. Oh yeah, I remember now. Sometimes people look at this and they think, I've got two data structures that are shared between some program and some interrupt handler. If I disable interrupts, manipulate the first shared data structure, re-enable, and then do some other stuff, and then disable, and then manipulate the other shared data structure, and then re-enable, I'm okay. Well, maybe, maybe not. You need to think about if those two operations are related, and if somebody wants to see changes to one, they should also have seen the changes to the other. In those cases, you need to guard the whole thing. So you have to think about the right granularity of your critical sections for correctness. So if you have multiple things to manipulate, don't try to make your system more efficient by just guarding each little manipulation. You may need to guard the whole thing. So again, you need to sit down and analyze whether or not it's okay for some people to see changes to one thing but not the other. Those are the kinds of things you need to think about in implementing these concurrent systems. Okay, now we mentioned briefly spinning. Okay, and so it is possible to disable interrupt handling on all the processors. You don't do it with the CLI instruction. Remember, we have these APICs on the processor, and what you do is you can tell all the processors to disable their APICs. So now nobody's getting interrupts delivered. Okay? You can do that, but it's a terrible approach, and you really only do it when you absolutely have to. So we talked briefly about spin locks, which is basically if the lock is available, grab it, otherwise spin until it becomes available. Okay? So we call that spinning because you're sitting in a tight loop checking on the lock. Okay, so you're checking on the lock maybe a few clocks, you're giving an interval of a few clocks, and then you check on it again, interval of a few clocks, you check on it again, and so forth. So you're really checking it fast, which means you're kind of expecting that it's going to become available really quickly. They only make sense on multiprocessor systems where the lock is only going to be held for a very short time. Okay? And like I say here, the assertion is that they make no sense on a single core system. Okay? Because either they're going to sit there forever, which defeats the purpose, or they're going to waste time. Those are basically your two options. You're either going to waste time or you're going to lock up the system. Those are basically the options when you have a spin lock. Okay? So the scenarios that prompt spin lock use is that you cannot context switch away, i.e. you're in an interrupt context. Now, that's not the only situation. I'll talk a little bit about that. The other scenario is that you expect the lock to be held for a very short period of time, and you don't want to context switch away from the process or the thread. Okay? It could be either one of those. You'll notice that the second one doesn't necessarily require interrupt context. Okay? How many people here have used Postgres? Okay, so if you've used Postgres on a multi-core system, you're using spin locks, actually, because the Postgres lock manager is pretty clever. What it does is when a transaction wants to acquire a lock, it spin locks for a certain period of time. Because the presumption is other transactions may be short and they may release their lock quickly, so why actually context switch away from that process? Why trap into the kernel? Why do all of that work when the lock may be released right away? So you spin for a little bit of time, and then if you don't get it, then you go ahead and switch to passive waiting. Okay? So that doesn't require being in the kernel. That doesn't require interrupt context. It's just a good idea when you're in a multiprocessor system. Okay? But the other scenario that we care a lot more about in the operating system is that we may actually be in interrupt context and we can't actually context switch away. Okay? So we can use those for concurrent access. Really simple example is timer interrupt. I kind of gave this example before, so we'll go through it quickly. Each CPU is executing its own timer interrupt handler. Their timers are not necessarily synchronized, so not a big deal. That's fine. But the interrupt handler may need to access shared state. And maybe this is the preemption interrupt, so that we can actually kick a process off the CPU, switch to another process. So since we do have shared state, we need to have a critical section to manipulate it. And so we can just acquire a spin lock. And if one processor is spinning on this lock and another processor is holding the lock, well, it's able to progress. It will eventually release the lock. So this spinning guy is able to eventually acquire the lock and go on. Because nobody ever passively waits. Everybody will eventually proceed. Okay? that's the idea behind using spin locks on a multi-core system. Now, are there any questions about this specific example? Okay. If control paths can be nested, then you can get into all kinds of hurt. So spin locks, you can see, are a very powerful tool, but they're a very limited tool. Okay, so let's say I have nested kernel control paths, and I have some state that's shared between a trap handler and an interrupt handler. And I decide to guard that state with a spin lock. Okay, the interrupt handler can interrupt the trap. The trap handler probably won't be able to interrupt the interrupt handler. Who calls traps from interrupt handlers anyway? That doesn't make any sense. So the trap handler acquires a spin lock. Good, I'm using spin locks. I'm trying to be clever. Right? So the trap handler acquires a spin lock. It starts accessing the shared state, and then the interrupt goes off. So what happens? The interrupt handler tries to acquire the same spin lock. Can it? The answer is never. It can never acquire the spin lock. This is a classic deadlock scenario, actually. It's just that one of the resources is the CPU, which is kind of fun. Okay? We have a resource guarded by a lock, which the trap handler holds. It needs the CPU to proceed so that it can finish and then release the lock. The interrupt handler needs that resource, and it holds the CPU. So there's actually a cycle in the dependencies there. Okay? So basically the interrupt handler hangs, and your fan will probably turn on because it's actively waiting, not passively waiting. You probably have all, you've probably all heard your fan turn on. Probably not because of this, I hope. Okay, so what you have to do in the trap handler is disable interrupts and then acquire the spin lock. That should always go really fast because, I mean, unless you're on a multi-core system where somebody else holds it. Okay? So this is one of those interesting scenarios where if you're doing things and you have nested kernel control paths, you have to think carefully about what's allowed to overlap, and when it gets to execute, what resources may already be held. Okay? Now, I hope this doesn't scare you. To me, it's like super exciting and fun. Like there's all these puzzles when you write an operating system. And you have to think carefully about how to solve them correctly. Okay, questions? All right, so there's one example. So I've kind of beat this one to death. They're only useful on multiprocessor systems. They should only be held for a short time. That's kind of the whole point. Otherwise, you'd be much better off trapping into the kernel or passively waiting, something like that, incurring all the overhead of passively waiting. So, you're talking probably on the order of a few hundred instructions. If a few hundred clocks can go by before you acquire the spin lock, you're probably okay. Beyond that, you probably should actually switch over to passively waiting. If a critical section is only entered by control paths running on different CPUs, simple spin locks are probably fine because you'll never get that weird deadlock scenario that I talked about. If more than one control path on the same CPU can enter a critical section, you have to think very carefully about whether or not you need to disable interrupts before you acquire the spin lock. Okay? You probably could run into this situation if interrupt handlers are allowed to preempt each other as well. I'm going to leave that as an exercise for you because I'm lazy. Okay? You can think about that. Linux has a couple of different spinlock primitives because of these constraints. So you can see that spinlock IRQ and spinunlock IRQ disable and re-enable interrupts. Spinlock and spinunlock leave interrupts enabled. Okay? Or I should say they leave interrupt handling in whatever situation it might be in. I mean, if it's already disabled, then it'll just leave it disabled. Okay? But spinlock IRQ and spinunlock IRQ make sure that interrupts are disabled before they perform their operations. I'm sorry. Spinlock IRQ disables interrupts. Spinunlock IRQ re-enables interrupts. I should be more specific. Okay. So let's talk briefly about deadlock. There's a couple different ways to formulate it, but you can see that there's certain common themes that you have when you can encounter deadlock. And there's a lot of different systems that can deadlock. Operating systems happen to be one of those examples where it can deadlock. You try to design it so that it won't. Okay? And so the definition here, a set of processes is deadlocked if each process in the set is waiting for an event that only another process in the set can cause. Okay, well, so this is an event-based formulation. The event might be releasing the lock on a resource. Okay, so that's how you can take this event-based definition and turn it into a resource-based definition. It's not very difficult. But here are the requirements for deadlock. We have mutual exclusion, so we have resources that can be held in a non-shareable mode, and all of the resources that are held or all the events that can occur are mutually exclusive. I have a hold and wait approach, where I acquire a resource and I don't let go of it if I want another resource and I can't get it yet. So I could also have an approach where I say I want to acquire a resource, or I should say I acquire a resource and then I want a second one, and if I can't get it, I just release everything. That would violate hold and wait. Then I have no preemption, so if I have a resource, I get to hold on to it as long as I want. Nobody can tear it away from me. Okay? I get to choose when I want to release it. And then the final constraint that produces deadlock is that you have a circular wait situation. So the set of processes P1 through Pn can be ordered so that P1 is waiting for something from P2, P2 is waiting for something from P3, blah, blah, blah. Pn is waiting for something from P1. Okay? If all these four situations hold, then you have a deadlock. Okay? So that's really simple. That's not terribly complex. Why is this even valuable to know about? Well, it's when you have this set of requirements, then you can look at how do I design deadlock out of my system, or how do I break deadlock when it occurs. If I can preempt a resource, this is what databases do, then I can break deadlock, because if some process is holding a resource that's causing a deadlock, I just take it away from them, and then I can clear up deadlock. If I have hold and wait, well, I can have a process relinquish all of its resources, and then I break hold and wait, and then I don't have deadlock anymore. If I can break circular wait, then I can also break deadlock. Okay, so deadlock prevention. You engineer the system so that it never occurs. This tends to be what we need to do for these kinds of systems. So typically what you can do is impose, let me see if I talk about this here. Yeah, no preemption. So if a process can't acquire a resource, you relinquish all the other locks you hold. People don't normally do this because it's way too complicated. If you have multiple things and maybe you waited a while to get some of those things, then you definitely want to hold on to them. So it's not very practical. But circular wait is much easier to control. Okay? You just have a total ordering on all of your resources you want to lock. And as long as everybody follows the same total order, it is not possible to generate a circular wait. Okay? Everybody is always waiting for something that somebody else has, but then there's some guy at the end of the total ordering that's holding stuff and not waiting for anybody before them. So you basically never have any cycles in your wait graph. Okay? Okay, so yeah, like I say here, that's usually not imposed by the operating system automatically. It's the programmer has to do that. So you have to think, basically, to prevent deadlock. Okay? Then you have deadlock avoidance, where the system basically looks at what you're asking for and says, no, you're not allowed to have this, because it would cause a deadlock if you did. Okay? So that's an interesting scenario. Okay, let me go through this. I don't actually talk about the banker's algorithm, but the banker's algorithm, the reason it's called the banker's algorithm is because it acts like a bank. Banks try not to give you money if it would actually put them into a bad situation. Okay, so the bank carefully considers whether or not it has the assets or the resources to grant your request, and if it doesn't, it says no. So that's why it's called the banker's algorithm. You can read about that on your own. Oh, and these are always fun. You have wound wait and wait die. Okay, so if you have two processes, and typically you can order them based on whether or not they've already acquired resources or who started first or something like that. So we have an old process and a young process. Wound wait is that if the old process needs a resource that the young process holds, the young process dies. Yeah, we wound them. Okay? If the young process needs a resource that the old process holds, the young process waits. Okay? So that's wound wait, and then wait die is similar. If the old process needs a resource that the young one holds, the old one waits, and if the young one needs a resource that the old one holds, the young one dies. So anyway, these are basically two other approaches that will fail resource allocation requests so that you can actually avoid deadlock. Okay, and then of course there's deadlock detection and resolution, which we talk a lot about in CS122, so I won't spend very much time on that. Okay. All right, so these are various approaches to deadlocks. I'm not going to spend very much time about it. For us, what we need to do is think very carefully about the order that we acquire locks so that we can avoid deadlock. So we kind of prevent them in our programming. Okay, any questions about deadlock? All right. Let's start talking about a few simple locking primitives just to make sure that we cover them. Semaphores are extremely common and they're incredibly valuable. I love semaphores. They turn out to be so incredibly helpful for coordinating operations between threads or between processes. Okay? And so typically you have a process who wants to acquire a semaphore. We'll talk about what that means. And it will block. It will passively wait until the semaphore is available for that process to acquire. So you can't use them in interrupt context. That's not a surprise. You can't use mutexes in interrupt context either. And so semaphores have a count, basically, and you constrain it so that, for example, it can't be negative. So it can be 0, it can be positive. That's fine. And then you have a list of processes or threads that are waiting to acquire the semaphore. And you have two operations, wait and signal, or down and up, because that's basically how they're implemented. When you call wait, you try to decrement the semaphore's value. If it would go negative, you're not allowed to. Instead, you go into the wait queue. If the semaphores count, so if somebody calls signal, the semaphore count goes up, and if there's threads in the wait queue, you pull one out and you allow it to successfully acquire the semaphore. So the count goes back down, and that process is allowed to proceed. Okay. Edgar Dijkstra had some interesting names, mainly because they're in a different language, I guess. But you had try to decrease, okay, again indicating what the value represents, and then you had increase, okay, or the Dutch versions of those. I can't remember what nationality Dijkstra was. Maybe wrong. Okay, so anyway, that's basically how these things work. So you can think of the value as being how many times can I wait before I block? So you can initialize the semaphore to 5, you could initialize it to 1, you could initialize it to 0 if everybody should always start waiting by default, and then you just signal to wake people up. Okay. So simple version, while the semaphore value is 0, add the thread to the waiting list, passively block the thread, and when that while loop finally terminates, the semaphore value will be positive. You know it will not be 0 or negative, and you go ahead and decrement a value, and off you go. Okay. Signal, again, you add 1 to the semaphore's value. If the waiting list is not empty, you remove a thread from the semaphore waiting list and unblock it. So now it's able to proceed. So it would have passively blocked there, and then, in signal, you wake it up, and it suddenly sees, hey, the value's not 0 anymore, and then it decrements it, and it goes back to 0. Okay, so that's the idea. You guys did this in CS24, so it's not terribly complicated. But you do have to enclose those sequences of operations in critical sections. Okay? And obviously it's a little bit more complex than that, because when you passively wait, you need to exit the critical section so that other people can enter it, and then when you wake up, you have to re-enter the critical section. So it's a little bit more complicated than we have here. But I think it's straightforward to figure out. And there are various ways to manage the block threads. So you could always put them at the end of the waiting list and always take them off the front. That tends to be a very simple way of doing things. You could choose a random thread to unblock. That seems kind of over the top. But it's interesting because you don't really have very many guarantees of fairness here. Okay? It's certainly possible that somebody waiting can be preempted by somebody else who comes in and calls wait at the right time. So we don't really guarantee fairness with these data structures. Most of the time, these concurrency mechanisms don't guarantee fairness because it's more expensive to impose fairness than to just let it be unfair or possibly unfair or whatever. Okay? And that's fine. If you design your algorithm so that you don't care about every block thread getting access eventually, then who cares? You'll be perfectly fine with a partially fair or unfair concurrency mechanism. Okay, counting semaphores, so you can think of that value as being a count. How many times can you call wait without blocking? So you could say, how many instances of a resource are available? How many threads do I want to be able to run concurrently? Those kinds of things. Okay. And so we call them counting semaphores when they're used in that way. And you'll notice that it doesn't really ensure mutual exclusion. So, because you can have multiple threads or multiple processes call wait concurrently, and they'll all get access. And we looked at this example in CS24. It happens to be a really classic concurrency problem, the producer-consumer problem. What if you have one or more producers and one or more consumers, and they're running at various rates to produce and consume data? So how do we get those things to actually collaborate in an efficient way? So it's a very common, you run into this problem a lot in system implementation, it turns out. And so the simple solution we used in CS24 is you have one semaphore representing how much data is actually in the queue. So that tells you how many readers can try to read data before they start blocking. Okay, so a writer signals every time more data is added. You have another semaphore that says how much space is in the queue, so writers have to get access to write before they can write. And it will, again, passively block if there's no space available in the queue. Now, you might ask yourself, just as an aside, is this the most efficient way of creating a queue that passively waits both on readers and writers? And the answer is no. There's a couple of other more clever ways of doing it. But it's a very straightforward, comprehensible way of doing it. So not all that bad. We like things that are comprehensible. Okay, now, of course, we had two semaphores, and we have shared state, and those things need to be manipulated. But we said that when you have a counting semaphore, it doesn't ensure mutual exclusion. It just allows you to govern resource access. So we still need to have some way of guaranteeing mutual exclusion. We have to have some way of enforcing a critical section. And so we introduce a third semaphore to enforce mutual exclusion. Okay? And that allows us to govern the shared state within the bounded buffer to make sure that nobody can manipulate it. You know, it's non-atomic manipulation, so we need to guard it in a critical section. And we make sure that this semaphore will have a starting count of 1. So only one thread is allowed to grab the semaphore. All right? Now, when we use them in this way, we call them binary semaphores. Okay? So the maximum value of the semaphore is 1, and we can enforce mutual exclusion. Now, we're doing addition and subtraction. As we all saw in CS24, there are more efficient ways of guaranteeing mutual exclusion. Bit test and set, lock exchange, those kinds of mechanisms are more efficient than using a binary semaphore that increments and decrements a value. Okay, whatever. Okay, you can create more efficient systems. You know, if you just go in and create the specific tools. Okay, are there any questions about semaphores specifically? They're pretty straightforward, right? I mean, it's not terribly complicated. You've got a counter and you've got a list. How much more complicated can it get? Condition variables, which we won't talk about, actually are like a mutex and a couple of lists. It's only slightly more complex. We don't really talk about them, but you can figure them out on your own relatively easily. And I believe there's actually an implementation in the Pinto docs that you can look at and read about. So you have that to look at if you'd like. Okay, so since semaphores that are used as binary semaphores are a little bit expensive, we go ahead and use mutexes frequently to simplify the state management and make it more efficient. Okay? Now, if anybody ever asks, I don't know if anybody's ever asked you this question in an interview or something like that, but it's the kind of question I would ask in an interview if I were interviewing system programmers. What's the difference between a semaphore and a mutex? Okay, well, that's a good thing to think about. One of the huge differences is actually sort of a semantic usage difference. Mutexes, when they're acquired, are considered to be owned by whoever acquires them. So I own the mutex until I release it. Semaphores can be used in a much broader range of scenarios. Now, is this really like a constraint? A technical constraint or a limitation? No. It's just conceptually how people look at them. Semaphores, one thread can acquire a semaphore and another thread can signal the thread by, you know, what do we say? No, we say we can wait on the semaphore, so I'm waiting, and then somebody else signals me to wake me up. A really simple sort of poor man's condition variable. Okay? You'll run into this a lot in Pintos in these assignments. On Project 4, when you actually get into user space and system calls and all of this stuff, you'll have an exciting situation where you start a process and then you want to find out if it's terminated yet. Well, what if the startup process takes longer than the guy who's waiting, and he calls wait before the process is fully started? In those situations, your brain should always say, semaphore, I can use a semaphore. So you create a semaphore, count as 0, the parent waits, so he tries to acquire the semaphore, the child increments the semaphore after loading is completed and the process has started, or let's say the process is finished. Then you allow the interaction. So semaphores are a really great synchronization mechanism between processes, between threads. Mutexes are basically only used for enforcing mutual exclusion. Okay? All right, so yeah, they're typically formulated to block processes passively. So again, we have some queue associated with it, and because they passively block, I should say they block and make people passively wait, then they typically are not used from interrupt context. Okay? Any questions on this stuff? I know, like, this is a lot of knowledge, and as you use them, you'll start to realize, oh, this is how these things are useful, and you'll start to get a sense of how the tools are used. It's amazing. Semaphores are such a powerful tool, and mutexes are powerful too, but semaphores are really good for coordinating processes together. Okay, let's see. Yeah, we've only scratched the surface. That's basically like the two most basic things, but there's a lot of other stuff you could talk about. I mentioned barriers. I'm now talking about the multi-threading synchronization primitive. There's a lot of synchronization problems which are great to study. If I have time, which I doubt I will, so don't expect it, I would love to go through multiple solutions to the dining philosophers problem, which again you may have heard of. I can't even remember. What is it? You've got a table and philosophers around it. You've got a chopstick on the left and a chopstick on the right, so every philosopher has a chopstick between them, or every pair has a chopstick between them. And philosophers are either thinking or they're wanting to eat, and so before they can eat, they have to acquire both chopsticks. So design a system that allows all the philosophers to eat without starving to death. Okay. So it's a fun problem, and I think it was actually designed for an exam back in the day. And there's a handful of solutions that are really, they demonstrate various approaches to concurrency. Let's see, yeah. So there's a lot more detail on deadlock detection. If you're curious, you can take CS122 and see how databases solve this problem. It's very different. And then there's a lot of other things that we don't talk about. What is live lock? Well, that's in a situation where everybody can try to acquire, and if they fail, they go do something else. And because the attempts keep happening at the same time, nobody ever actually acquires the resources that they need. So live lock is a weird situation where it's deadlock, but everybody's still moving. Okay? Movement does not always indicate progress. And a few other things. Okay? So, are there any questions? All right, so what I want to do, we have about 3 minutes left, and I don't know if I'll be able to get through all this material, but I did want to throw it up here. I wanted to talk about thinking like a kernel programmer because it is very different from thinking like an application programmer. And I wanted to kind of point out some of these details here. It's not just that we're right near the hardware and we don't have very many abstractions to leverage, and we have to do a lot of our debugging in emulators and things like that. That's not really the only issue. The big thing with kernel programming is you have to focus on efficiency. And you'll notice that there's a lot of focus on efficiency because any little change you make, and you'll notice a lot of the things that are mentioned in the slides are not big changes, but since they're used throughout the operating system, they result in a big impact. And there's a couple of reasons. One is that we have fewer resources, and the other is that the kernel runs, it intervenes in everybody's life. So if we make the kernel incrementally better, there's a huge benefit to everyone because everybody benefits from it. Okay, a few details here. Managing a linked list of items. You'll notice that in an application, typically you separately allocate each node. You link them together. Yay, that sounds fine. Probably everybody here has done that at one time or another. Probably even this term. Frequently, the linked list elements hold pointers to other data structures that are also separately allocated. You do not do this in the kernel most of the time. First of all, you don't have a general purpose allocator. And we'll talk about kernel allocators for 2 lectures. It's really fascinating, all the solutions. Okay? We can't lose the space that you need to have to manage the heap. Okay? And also, it turns out that kernels typically only have a subset of data. They have a very limited set of data structures that they tend to need to dynamically manage. So we don't create general purpose allocators. It's not really a big point in having them in the kernel. So instead we fold that data structure management into the objects that need to be managed. And again, if you've done any of the third assignment, you've probably already started to notice this kind of thing. Okay? The list pointers point to the next list pointer. They don't actually point to the start of the data structure, which is really weird. One reason is because, well, I may have multiple kinds of data structures that need to be linked into linked lists. And of course, when you do this, you need to figure out where is the start of the data structure so that I can access the rest of it. And so there's actually little, what is it, list elem, I can't remember, or list entry. Pintos has a couple of macros for this kind of thing. And you basically know the pointer, and then you have to subtract the offset from the pointer to the start of the data structure so you can get back to the beginning. Now, it's a little bit deceiving, this picture, because A is actually at a lower address than B, and B is at a lower address than C, because typically the way C lays out data structures is the order of them in the struct declaration is increasing address values. Okay, so that's why we do this, subtract the offset instead of add the offset. It looks a little bit weird. Okay. Now, the other reason why we like to fold this into the data structure and just point to the next pointers in the list is that we may want to have multiple linked lists that tie our things together. Really common, unfortunately, which means you can traverse things in different order based on which list you start at. Okay? So that's one of those unusual things. Why do we do this? Well, the reason why is because we want to avoid dynamic allocation, if at all possible, because we really don't have that facility. We want to avoid the overhead of managing dynamically allocated memory. We want to do things as efficiently as possible. So we do this crazy thing. But thankfully, we can actually wrap it in macros so that all of this stuff is simplified. Now, another question, of course, is do we actually need to dynamically allocate memory? So we had this example, and you may or may not recognize that this actually corresponds to the thread data structure and how it's managed in the threads.c. You have the anchors of your lists are statically declared in the C file so that you can just access them. And these data structures are actually at the bottom of the thread stacks so that we don't actually have to dynamically allocate them. We just put them in the space that we have to set aside anyway for the thread stack. So you actually end up with no dynamic memory allocation at all. This is the reason why we do this stuff, because we don't have those facilities and we wouldn't want them anyway. Okay, here's another example, which is kind of near to my heart. Let's say that we need to manage a linked list of nodes, and we know that the list has a maximum size. So we know that there's a maximum number of elements that we need to manage, and most of the time that list will actually be full or mostly full. So instead of actually dynamically allocating the elements, why not just, again, set aside a region of memory that is large enough to hold all of the nodes we might ever need. Hey, guess what? Static allocation is fast. And then I can sort of link them all together into a linked list just within my array. So now you've thrown away your heap management space overhead, and allocation is really easy. You know, you just go and take the first node off the free list, and you've got your next node. So that's way faster than calling into a heap allocator. Okay? This is a really common approach in a certain kind of page table management. Clock. Yeah, it's called the clock page eviction policy. We'll talk about that in quite a few weeks. So, but anyway, this is a very common approach for implementing that. Okay, interrupt handlers. So this is also important. We talked about this briefly last time, that you have a choice between working in interrupt context versus in process context. If you do it in interrupt context, everybody's affected. If you do it in process context, only that process is affected. So again, what should you choose? Well, it's really easy. You typically want to make one process wait instead of making everybody wait. Okay? There's a couple of examples in the third project, the timer sleep. So this is why it's a good example. I'm going to go ahead and skip over this just because of time. We're already late. But you can read about that. Okay. And yeah, you can look at that as well. I'm going to just go ahead and skip all of this. So basically, the whole point of kernel programming is that you need to think about efficiency much more than you do in a regular application. Okay? And admittedly, these things generate only small savings. But since this is the operating system and everybody has to use it and everybody's affected by it, a whole bunch of small savings add up really fast. And so these are the kinds of things that kernel programmers think about a lot. Can I avoid dynamic memory allocation? Can I move computation out of interrupt handlers so that the interrupt handler is really short and fast and into process context? Are there constraints on system behavior that I can exploit? And can I reuse fields or data structures for multiple purposes? So you'll have to read the slides corresponding to those to see the specific examples. But there are frequently solutions that are still maintainable, but give you significantly improved performance that you can leverage. So I wanted to make sure to include some discussion of that. It's like, why the hell are we doing this weird stuff? And this is the reason why. It actually has a big impact. Okay, if you have any questions, please talk to me afterward because I don't want to take up too much time. Next time, we'll talk about read, copy, update.